In today's lecture, we are going to deal with power series. So what is a power series? A power series is an expression of the following form: summation n from 0 to infinity an times x to the power n. Here an's are some given numbers, some real numbers, so it's a sequence of real numbers, and x is a variable. So if this sum makes sense, I can view this as a function of x. Okay, and what we will like to understand is that for which x this function makes sense. So to start with, this formal expression, because I don't know the meaning of this, is a power series in x. Notice that if I give a fixed value to x, then what it gives me is an infinite series. And now we very well understand what is the meaning of convergence of an infinite series. So we can check x by x if we can. That is, put a value of x in the series, you get an infinite series, check that whether it makes sense. Okay? So to start with, let me look at some examples. So first let us look at this series, summation n from 0 to infinity factorial n times x to the power n. So here an is equals to factorial n. So this is a power series in x. Another example would be summation n from 0 to infinity just x to the power n. That is, here an equals to 1 for all n. Another example would be n from 1 to infinity. Well, I can still take n from 0 to infinity divided by factorial n these times. So here an is 1 by factorial n for all n. What I will like to test now, one by one, is for which x these three infinite series which I have written, they make sense. So we start with example 1 first. So here the infinite series is summation n from 0 to infinity factorial n times x to the power n. So I fix x and I want to check for which value of x this would make sense. So I try to apply my ratio test. So that means I have to look at modulus of the n plus 1th term, that is n plus 1 factorial times x to the power n divided by the nth term, that is factorial n times x to the power n, and then I have to look at the limit as n goes to infinity. Then what I get is limit n going to infinity modulus of n plus 1 times x. Notice my x is fixed, so it can be taken out of the sum, this limit. So it is mod x times limit n going to infinity. Now this limit will certainly be infinite. It does not exist finitely. So that way I don't get any x, it looks like, for which the series makes sense. Notice that this limit does not exist if mod x is not equal to 0, that is x not equal to 0. On the other hand, what happens if I choose x to be equal to 0? Then look at the terms of the power series. It is factorial n times x to the power n. But if I choose x to be equal to n, then all the terms of the power series is 0. So that certainly converges. So the conclusion then is that only for x equal to 0, the power series converges. Now let us look at example 2, that is summation n from 0 to infinity x to the power n. Now if I apply ratio test, or by my knowledge whatever I know, that this is a geometric series. This is a geometric series and converges for mod x less than 1 only, because if I take mod x to be bigger than or equal to 1, the series does not converge. So this power series, it makes sense as long as modulus x is strictly less than 1. Okay? So at least if I choose my x in the open interval minus 1, 1, then this series certainly represent a function. I can write fx equals to this sum as long as x is in minus 1, 1, otherwise not. If you look at the previous example, if I want to write fx, I cannot unless I choose x only to be equal to 0. Let us look at the third example now. Here the power series was summation n from 0 to infinity x to the power n by factorial n. Okay. So again, to understand the behavior of the series for different possible x's, all I do is I look at the ratio test. So that means x to the power n plus 1 divided by factorial n plus 1 into factorial n divided by x to the power n modulus, I have to take the limit as n goes to infinity. Well, I choose x to be not equal to 0 also, otherwise this x to the power n in the denominator will be a problem. But if I choose x to be equal to 0 in the series, you anyway get 0. Well, not quite. If I put x to be equal to 0, then all the terms bigger than the first term, that is the n equal to 0 case, they are all 0. It is only the first term which survives. That means I can write this series, if I look at it clearly, it is 1 plus x square by factorial 2 and so on. Notice that if I put x to be equal to 0, then I get x equal to 0 implies summation n from 0 to infinity x to the power n by factorial n is equals to 1. So the problem of convergence is not there if x is 0. It is only there when x is non-zero. So in that case I can certainly divide and go to the ratio test. What I get in this case is limit n going to infinity x divided by n plus 1, then the modulus. Again, x is independent of n, so it is mod x times limit n going to infinity 1 by n plus 1, which is 0, whatever my x is. Notice for convergence in the ratio test, the limit is strictly less than 1. In this case I get 0, which is strictly less than 1. That means this series converges for all x, whatever x you choose. So that means given a power series summation an x to the power n, for which x it will converge, that certainly depend on the coefficients an I am choosing. It may happen that it does not converge for any x non-zero. It might happen that it converges for all x. It might happen that it converges for some x. Now let's go to more deep into the power series. It can usually never happen that you have discretely many x's for which the power series converges. The convergence, if it happens, it will always be on some interval. If you look at the example which we were doing in 2, the x's for which it converges is modulus x less than 1, other case is x equal to 0, it can happen that it converges only on a point and nowhere else. In the third case, I got that it converges for all x. So except a point, it is always an interval. So let's go to the next theorem, which will explain that why such a thing is happening. That means if convergence happens at non-zero points, it is always happening in some interval. So the result is this. Suppose summation n from 0 to infinity a n x to the power n converges for x naught, a particular point. Okay, then the series converges absolutely for any x such that mod x is less than. So what does this mean? It means that the series converges in the interval minus x naught, x naught. I am assuming my x naught is positive, so minus x naught is negative, or it is the other way around. If your x naught is negative, that can be considered as minus x naught, so x naught is positive in that, minus of x naught is positive in that case. But what is happening is that whenever you have some point, so in picture what it means is this, let us say 0 here and x naught here, and suppose the power series converges at this point, then immediately what you know is, look at minus x naught which is here, then every point between minus x naught and x naught, whatever point you choose between minus x naught and x naught, the power series converges. Not only that, it converges absolutely. That is the reason why I am always getting intervals as the domains of convergence. That means I am always getting intervals of x's for which the power series converges. Now there is a second part. It says that if summation over n a n x to the power n diverges for some x1, then summation over n a n x to the power n diverges if mod x is bigger than mod x1. Okay, so once you get one point where it diverges, then quickly what you can do is look at the interval with the endpoints of that point and minus of that point. That is, if the point is x1 where the power series does not converge, look at the interval minus x1, x1. Look at this closed interval. Outside that closed interval, certainly the power series is going to diverge. That is what it seems. Okay. So let us come to the proof of this. So first I try to prove 1. So what I know that summation n from 0 to infinity a n x naught to the power n converges. That is my hypothesis. And if an infinite series converges, then its terms has to be bounded, because I know that after some stage all the terms go to 0, and before that stage there are anyway finitely many terms. So the sequence of terms of an convergent infinite series is always a bounded set. So this implies there exists some m bigger than 0 such that mod an x naught to the power n is less than or equal to m for all n. Okay, fine. Now I am going to use a simple trick. I look at modulus of an x to the power n. Let me assume that x naught is non-zero, because if I assume x naught is equal to 0, then the theorem is trivial. So I assume x naught is not equal to 0, because if x naught is equal to 0, then mod x is less than modulus of x naught, means x is also 0. Then the power series obviously converges. So the point is, if x naught is non-zero, then what happens? So I look at an x to the power n. I write this as modulus of an x naught to the power n into x by x naught whole to the power n. If I separate the modulus, it would give me, using the previous inequality, that modulus of an x naught to the power n is always bounded. It is less or equal to m times mod x by x naught whole to the power n. Now notice, as modulus x is less than modulus of x naught, this implies modulus of x by x naught, if you allow me, I will call it r, well, let me call it q instead of r. This is strictly less than 1. And that means what I got is that mod an times x to the power n is less than or equal to m into q to the power n. Now as q is less than 1, I know that summation n from 0 to infinity q to the power n converges, being the geometric series. If I have a geometric series where the common ratio is less than 1, then the geometric series converges. That we have already seen. Using that, it then follows by comparison test. This implies by comparison test that summation n from 0 to infinity an x to the power n converges if modulus of x is strictly less than modulus of x naught. Okay. Now let us go to the part 2. But it says that if at some point x1 it diverges, then for mod x bigger than that modulus of x1, the power series diverges. So let me write down the hypothesis first. The given hypothesis is summation n from 0 to infinity an x1 to the power n diverges. Let me choose an x. Let x be such that modulus of x is bigger than modulus of x1. I want to prove that summation an x to the power n diverges. To prove that, summation n from 0 to infinity an x to the power n diverges. This I need to prove. If not, then summation n from 0 to infinity an x to the power n converges. Okay. But notice that modulus of x1 is less than modulus of x, and I know that summation n from 0 to infinity an x to the power n converges. Then I apply the first part of the result. Since modulus of x1 is less than modulus of x, and summation a n x to the power n converges by the first part, this implies that summation n from 0 to infinity a n x1 to the power n converges absolutely. In particular, that means it converges. But my hypothesis says that summation a n x to the power n diverges. So that is a contradiction, and this contradiction happens because I have assumed that n from 0 to infinity a n x to the power n converges. That cannot be true. That is why the contradiction happens. And that certainly proves our result. Now I am going to define a concept which is the most fundamental one in power series, that the radius of convergence. So we say, let us look at all the x for which the power series converges. So I am going to look at mod x such that n from 0 to infinity a n x to the power n converges. Notice that it can happen that a power series a n x to the power n, it converges for x, but it does not converge for minus x. That can happen. We will see some such example. I look at all the x's for which a n x to the power n converges, and then I look at their modulus. And then I look at the supremum of this. I call it R. Now notice here, this set is an unbounded set. So if the set is unbounded, then I take my supremum to be equal to infinity. So let me note it here, that if the set is unbounded, that can also happen. Consider R equal to infinity. This R is called the radius of convergence. Now, the very definition implies certain things. Suppose, I will call it a note. Suppose mod of x naught is less than R. Then I want to show that this implies summation n from 0 to infinity a n x to the power x naught power n converges. How does this follow? Since modulus of x naught is less than R, there exists y in the set such that modulus of x naught less than modulus of y less than R by the definition of supremum, and summation n from 0 to infinity a n y to the power n converges, or a n minus y to the power n converges. One of these has to be true. But then apply the condition 1 of the previous theorem, that modulus of x naught is less than modulus of y, and summation a n y to the power n converges, or summation a n minus y to the power n converges. Whoever converges, I will consider it as y, and modulus of x is less than modulus of y. So summation a n x naught to the power n also converges by one of the previous theorem. So this implies summation n from 0 to infinity a n x naught to the power n converges. In fact, I am writing it this minus y to the power n for extra clarity. If I just write that there exists y such that modulus of x naught is strictly less than. Notice here, for extra clarity, I am writing minus y to the power n, but minus y actually can be considered also as y. What is the statement after all? It says that there exists an y such that modulus of x naught is less than modulus of y, which is strictly less than r, and summation a n y to the power n converges. That can as well apply to minus y also. So if it is y or minus y, I can just choose as one of them. Okay. So anyway, it follows that if I take a point x naught whose modulus is less than the radius of convergence, then the power series certainly converges there. The next observation is, what happens if modulus of x is bigger than r? That is, it is bigger than the supremum. Okay, suppose summation n from 0 to infinity a n x to the power n converges. If this happens, then by the definition of the radius of convergence, I will get that this implies that the radius of convergence must be bigger than or equal to mod x, because radius of convergence is supremum of all the mod x's for which summation a n x to the power n converges. So that would mean, since mod x is one such, I already have an x for which a n x to the power n converges, the radius of convergence must be bigger than or equal to mod x. But I already said that the radius of convergence is less than mod x. This implies a n x to the power n then diverges. Okay, so a fairly clear picture is coming out. So I draw the real line. This is 0. Since r is the supremum of modulus of x's, it's a positive number. Well, it's non-negative. I cannot always say it's strictly positive. I look at r, then somewhere here is minus r. Okay, then at all the points inside, the power series converges. And all the point after r, here the power series diverges. Here also the power series diverges. Only thing we did not talk about is what happens at r or minus r. Okay, for that I would look at examples. So look at this example now. Let us consider this power series, summation n from 1 to infinity x to the power n divided by n. That is, here a n is just 1 by n. We will like to find out the radius of convergence r, and we will like to investigate the behavior of the power series at r, okay, and of course at minus r. So first notice that if x equal to 1, then the series is summation n from 1 to infinity 1 by n, which diverges. Okay, and if I take x to be equal to minus 1, then summation n from 1 to infinity, I get minus 1 to the power n by n, which by Leibniz test converges, because this is an alternating series. Then if I apply my previous theorem, what should it tell me? What should be the radius of convergence? You see, what is the supremum of the x's for which it converges? Now, if I take any number x whose modulus is bigger than 1, there the series cannot converge, because at x equal to 1 it diverges. So all the x's for which the series can converge by the previous theorem, must satisfy modulus of x is less than 1. So this implies the series converges if modulus of x is less than 1, that is by the previous theorem. Okay, that means theorem, the first theorem 1 and 2 which I am applying. Now if you don't believe this, what you do is you just go for ratio test. You just look at limit n going to infinity modulus of x to the power n plus 1 divided by n plus 1 into n by x to the power n. That would give me modulus of x times limit n going to infinity 1 by 1 plus 1 by n, which is certainly mod x. So this less than 1 implies the series converges by ratio test, which I already have. So that means radius of convergence is equals to 1. But notice, at the radius of convergence, that is when r equals to 1, the series diverges. But r equal to minus 1, that means minus r, there the series converges. So the situation what is coming out is precisely like this. This is 0, this is r, this is minus r. So the possibilities are this. Certainly inside the series converges, no problem about that. This is the region mod x less than r. This is the region mod x less than r. Outside I have mod x bigger than r. So this is where divergence happens, here convergence. Now it can happen, now anything can happen for these quantities an r to the power n and an minus r to the power n. It can converge, it can diverge. That means both of them can diverge, both of them can converge, one of them can converge, other can diverge. So I gave an example of x to the power n by n, there r was equal to 1, and for that I have seen that for r equals to 1 the series diverges, but for minus r it converges. So at the radius of convergence anything can happen. Okay, you have no hold on that situation. Series can converge, it can diverge, and there are two ends because it's an interval after all. But what you know is that inside that open interval the series always converges, and outside that open interval, outside that closed interval, I should be careful here that if you look at the closed interval minus r, outside that the series always diverges. So I will note it here that in minus r the series converges. And in the complement of the set minus r, if that makes sense, the series diverges. Notice that this second situation, it does not occur if you know your r to be equal to infinity. So for example, if I look at the series x to the power n by factorial n, as I have observed already, n from 0 to infinity, in this case r is infinity. Okay, that means it converges for all x. So if r is equal to infinity, then the second situation doesn't make sense. Okay, so with this we finish our discussion on the elementary properties of power series. Now we are going to tell you certain methods of how to find the radius of convergence of a power series. So now let's try to see how to find r. I will tell you one method of finding r. It will work in most of the cases, but certainly there are certain cases where it will not work. So I look at the series summation n from 0 to infinity an x to the power n. The idea is just to use somehow the ratio test. So I look at the quantity, limit n going to infinity, a n plus 1 x to the power n divided by a n x to the power, plus 1 here, x to the power n, modulus of that. So this is modulus of x times limit n going to infinity, modulus of a n plus 1 divided by a n. I said in most of the cases it will work. What I meant is that all these n's are non-zero, because if there are infinitely many n's for which n's are 0, then it would be a bit difficult to apply this test. Okay. For example, you cannot directly apply this test if you know that a of 2n is 0 for all n. That means all the even position you have 0, so you cannot divide. Okay. You can apply this test if you know that after some stage all the terms are non-zero, then it will go through, but otherwise not. In that case you have to use certain tricks. Anyway, let us say suppose all the n's are non-zero, then I look at this limit and let us say L is this limit. L is limit n going to infinity, modulus of a n plus 1 divided by a n. Okay. Assume that this is non-zero, suppose so, then this implies that summation n from 0 to infinity a n x to the power n converges if L times mod x is strictly less than 1. This is by ratio test, and diverges if L times mod x is strictly bigger than 1. That implies that the series converges if mod x is less than 1 by L, and diverges if mod x is bigger than 1 by L. That certainly implies, by the definition coupled with theorem 1, that radius of convergence is equals to 1 by L. So let us again look back. If you have a power series where all the n's are non-zero, look at limit n going to infinity modulus of an plus 1 by an. If that limit is non-zero, then 1 by that limit is the radius of convergence. The problem happens if some of these n's are 0 and this limit does not exist. Those are complicated power series for which these tests will fail, but there is an analog of this result which I have done here using the root test. In most of the cases that will work, but in most of the practical situations you will find out that it is the ratio test analog of finding the radius of convergence which works, which is precisely what I have described here. That is, you look at the coefficients, form the terms an plus 1 by an, look at the limit, whatever you get, if that is non-zero, look at the reciprocal of that, that gives you the radius of convergence. Now, equipped with the knowledge of power series, I am going to talk about Taylor series, which is a power series which we already have encountered with. Let us talk about the convergence of Taylor series. So let us recall first about Taylor polynomial of a function. Of a function around 0, let us say. It's usually called the Maclaurin polynomial about 0. What is that? It is, we have proved that if f prime up to f n minus 1, these are all continuous on AB, and Fn exist, then I can write Fx equal to Fa plus f prime A into x minus a plus f double prime a x minus a whole square by factorial 2 plus f n minus 1 a x minus a power n minus 1 plus n minus 1 factorial plus the last term, that is fn. Instead of a, here we have c, which certainly depends on x. It will also depend on n times x minus a power n by factorial n. This is the Taylor polynomial about a. So put a equal to 0. This is called the Maclaurin polynomial or the Taylor polynomial for simplicity. So in that case, what happens is I get fx equal to f0 plus f prime a times x plus f double prime, f prime 0 times x plus f double prime 0 times x square by factorial 2 and all that. So a equal to 0 means fx equal to f0 plus x f prime 0 plus x to the power n minus 1 by n minus 1 factorial into fn minus 1 0 plus x to the power n by factorial n into fn at c x n. So the point c which we are getting here, it depends on x as well as n. Now suppose f is a function for which all possible derivatives exist. Suppose the situation is f has derivatives of all orders. Then if you just go on writing the Taylor polynomial which you are getting for all n's, you immediately get a power series, because what you are going to get is f0 plus f prime 0 at x. I can look at all derivatives, so it will go on plus fn 0 times x to the power n by factorial n and so on. So in short, I get summation n from 0 to infinity fn 0 into x to the power n by factorial n, with the understanding that f00 is just f0. Okay, so this is a power series. Now you can certainly ask that for which x this power series converges, and if it does it converge to the function? Well, the bad news is that there are functions for which this series makes sense, that for all x it converges, but it does not converge to the function. That can happen. But for most of the functions which are good functions, for that we will see that many of those functions, this Taylor series exists and it is equal to the function. So first the bad thing, so we can look at an example. It is kind of a difficult example to conceive, but it is true that I look at this function fx equals to e to the power minus 1 by x square when x is non-zero, and it is 0 at x equal to 0. What happens is, if you use L'Hopital, this implies that f prime, the derivatives of f at the point 0 exist. So whatever derivative of f you look at, it's 0, at 0 it exists, that is fn 0 exists. Not only that, it is always equal to 0. Okay, this is true for all n. This is not very difficult to show that it happens. So this function has the property, it has derivatives of all order existing at the point 0, and at the point 0 all those derivatives are 0. So if you look at then the Taylor series, that is summation n from 0 to infinity fn 0 into x to the power n by factorial n this is always equal to 0 because all the fn zeros are 0. So it cannot be equal to fx for all x because the function is non-zero. So if you have a function, so this is a particular example of a kind of a function which has the property that it has derivatives of all order, but at the point 0 all its derivatives are 0. Then for those kind of functions you can always write down the Taylor series around 0, but it doesn't make much sense. You will always get 0. That is not the function fx. But for certain other functions the Taylor series exists. I will show you some such example. Look at the function, the most famous one, fx equals to e to the power x. It has derivatives of all order, and f prime at x is e to the power x, f double prime at x is e to the power x, it is always e to the power x. Okay, for all n. So then what does the Taylor series look like? Summation n from 0 to infinity fn 0 into x to the power n by factorial n. You can see from the previous calculations that fn 0 is e to the power 0, which is 1. I get summation n from 0 to infinity x to the power n by factorial n. This power series we have encountered before. The radius of convergence of this power series we know is actually equal to infinity. So for every x it converges. Now I want to show that this converges to e to the power x. So what is the idea? You look at modulus of fx minus summation n from 0 to m fn 0 x to the power n by factorial n modulus. Okay, what I want to show is that this goes to 0 as m goes to infinity for each x. Okay, that will prove that the function fx is equal to the power series. Now what to do with this inside thing fx minus this summation n from 0 to m? Well, I know from Taylor's theorem that this is nothing but modulus f of m plus 1 at a point c m plus 1 x. The point depends on x as well as m plus 1 divided by into x to the power m plus 1, where x is fixed. Okay. Now if I write down all the quantities here, what I get is e to the power c m plus 1 x divided by m plus 1 factorial, because all the derivatives are e to the power x. So at the point cm plus 1 comma x, it is e to the power cm plus 1 comma x times x to the power m plus 1. But on c we have the property that 0 less c less x. Well, this c is cm plus 1 comma x. So that means this whole quantity is lesser or equal to e to the power x into x to the power m plus 1 divided by m plus 1 factorial. Now this is something which we have seen before, that as m goes to infinity, this goes to 0. That means the function fx equal to e to the power x is represented by its power series. So now I can finally write that this is summation n from 0 to infinity x to the power n by factorial n. So in general, if you want to show the Taylor series of a function at a point x converges to the function, all you have to do is to prove that modulus of fx minus summation n from 0 to m fn0 into x to the power n by factorial n limit m going to infinity is equal to 0. That is, in other words, you have to prove that limit m going to infinity modulus of f m plus 1 at c m plus 1 comma x times x to the power m plus 1 divided by m plus 1 factorial. This is by using Taylor's theorem, that this quantity is equal to 0. If this happens, then at the point x the function is given by its Taylor series. That is, you can write then that this implies fx equals to summation n from 0 to infinity fn0, if f has differential derivatives of all order, of course, x to the power n by factorial n. Okay. So this is the method. We have done it for fx equals to e to the power x. Now I will leave it as an exercise to check that if fx equals to sin x, then the Taylor series of f of f around 0 converges to the function. So to prove this, all you have to prove is whether this is true. Should not be very difficult, because fm plus 1 you can find out given the function sine, and then try to estimate and see whether the limit goes to 0. So with this we finish our discussion on power series and Taylor series.